Okay, I would like to tell you about how Gauss's law can be used to find the electric field due to a slab of charge. Okay, so let's take a look at this slab of charge we're talking about here. That's a cross section of a slab that goes a long way that way, and this way, and that way, and this way. In other words, if you think of a slab or a piece of wood that's charged, and charge is embedded throughout it. Okay, so we're looking at this like in this fashion. So there it is. But this piece of wood is going to go on a long way in all the dimensions except the direction of the flat surface, the greatest surface area. That one is actually going to stop right there. So if that's positive charge is embedded throughout and it's in that position, then if I put a positive charge just above it, like not at the surface but just above it, then if it would be pushed by all this positive charge straight away. So the electric field is straight up on the outside, and below it it's straight down. So like if we saw it down here, right there, it would be pushed straight down. But somewhere in the middle, like if I looked at like this right there, so a spot like right there, the field is straight up still. So, ooh, I have a very leaky pen here. All right, so let me get rid of that. And so there's our slab of charge. And let's see, I'd like to find the electric field at P1. Now, the electric field's magnitude at P1 is the same as the electric field at P2 if they're the same distance away from the center. This is the center. 0 is the center. All right. Now, what I'm going to do is to find the electric field at P1, I'm going to make a cylinder that starts right there, and it's going to go right straight down to the center. Now at the center there is no electric field. So right at the center there's no field there because which way would you think a positive charge would get pushed? Straight up or straight down? The answer is it wouldn't be pushed either way. It'd be pushed in up and down equally, so that means it'd be 0. Okay, so that's a cylinder, and I want you to see that there's no flux coming out the sides of that cylinder. It's the only flux is out the top. There's no flux out the bottom because there's no field, no electric field along the center line. And there's no flux out the sides because all the field lines are heading that way. They're heading straight up. So, you know, if this is a little dA right there, if that's the direction of dA, then the field going straight up would put no flux there. E dot dA would be 0. And so we're left with a very simple equation this out. Now let's say that the charge density of all these charges embedded in there is rho naught. That's the charge per volume. So rho is the charge per volume, and that's a known. So rho naught is the charge per volume, and that's a known. All right, so let's apply Gauss's law then. The charge enclosed, well, Gauss's law is the charge enclosed, the total charge enclosed, over epsilon naught is equal to the closed surface integral of E dot dA. All right, so the charge enclosed would just be the volume of that cylinder. Let's call this area A. We don't have to give it a radius. Let's just say that that top area is A. And then the volume would be A times this distance Y. I'm going to call that Y, the height that it is above from the center line. And so the volume is going to be just A, the area, times Y. So the charge enclosed would be rho naught times the volume, V, but V is going to be A, the surface area of that cylinder, times y, all over epsilon naught. Okay, that's equal to, now there's only flux. We can get rid of the dot product because the only place where there's flux, the dA is in the same direction as the E. We can pull the E out of the integral because why would we expect the E to be any different here than here than here than here than here? It's the same at every location. And when I add up all the dAs, sure enough, I just get A. So the electric field, if we cancel out the area, the top area of this thing, the electric field is just going to be, I'll put that down here, is going to be rho naught times y over epsilon naught. That's what that's equal to. We could have made our Gaussian surface come all the way down to here if we wanted to. And we could have reasoned that the total flux is, there's just as much flux out the top as there is the bottom, because there are field lines that way. Let's see what that would have looked like. That would have been, that would have made our cylinder 2y, since it would be y up and y below. That would be 2y. So let's see how that would work. The total charge enclosed in that big cylinder is rho naught. So that would be rho naught times the volume, A times 2y. That's the real height of that cylinder, all over epsilon naught. That's equal to the closed surface integral of E dot dA. But now we have flux out the top and the bottom. So when I pull the E out, because E is the same here as up there, there's only flux out the top and the bottom, then and add up both A's, I get E times 2A. That's equal to rho A 2y over epsilon naught. I'm going to get rid of the 2A and the A2. And as you see, we're left with the same equation. All right, I still need to tell you how to do a different problem than this. I still need to tell you how to do one that's just a flat plane. But first, let me just reiterate then that in a slab, the electric field, if it's going for a long way that way, if that slab is going a long way that way, and the slab is heading that way for a long way, and this way for a long way, that the electric field, if that's the center, the electric field right here is straight up. The electric field here is straight down. Apparently, it looks like as you go up more and more and more, if we look at our equation, it looks like if we go up twice as high, we get twice the field. So the field strength gets greater and greater as you go. Like if I were very close to here, then it would be a smaller field. You see how that's being shown that with this equation? If I make y closer to 0, then the field is, the electric field is proportional, directly proportional to how far you are from that center line. All right, we'll see you in the next video for planes of charge like that. That won't take very long. See ya.